Welcome back to Mass Spec. We got a ketone for you today. We'll see how ketones can break up in a mass spec machine. We looked at lots of different functional groups. Each one is unique, but each type of functional group has a certain pattern, right? Then it breaks up in, and so that's what we're going to look at. What does a ketone do inside the machine, or what does the machine do to the ketone? Let's look at it. All right, so here when it goes through the machine, it's going to be bombarded with high energy electrons, and the most vulnerable, I know there are pi electrons here and lone pairs here, but lone pairs are kind of exposed and they just take them out. All right, so here's your electron coming in, high energy, and taking this off. And so you're going to have a electron hole, which is what pretty much we call a positive charge. So here, just going to hit one of them, it's just pretty random. And so now you have a positive hole, and that is going to be your molecular ion peak. And that will be the same as the molecular weight, which is going to be 100, because the charge is 1, and so therefore m over z is going to be 100, and that is what you see. Ketones typically have a very strong molecular ion peak, unlike alcohols. All right, let's look at what could happen. What are these fragments here? 29, 43, 57, that almost sounds like alkane. So this could be ethyl, propyl, and butyl. But we haven't really seen 71 before. So let's take a look at what could 71 be. And there's a tiny 72 peak, and we can see what those could be. All right, so let's go about breaking it up, seeing all the possibilities. Now, when you have a carbonyl, the next carbon is called the alpha. Okay, and you have two alphas here, so they're both fair game. So this is alpha, beta, gamma here, and so you can see you can get alpha cleavage, gamma cleavage. A lot can happen. All right, let's start by doing an alpha cleavage. Now, as I said, there are two places. You can do it here or here. Let's say this is A, and let's say this is B. A, so A can have, you can have your lone pair and a radical, and that's going to be really unhappy up there. It wants to grab an electron, so you can either do A or B, and let's do A. So here you can take this, bring this over here, and split them up. If you do that, you are going to get this going away as a radical. So that is going to be a CH3, CH2 radical. That's 29. So if you take 29 out of 100, that's just going to be your 71 right there. Okay, so here is your remainder of the molecule, and that is going to have, well, now that you've made a triple bond, that's going to be sp, which is going to be 180 angle. You only have one lone pair left on that, and if you take the formal charge of this molecule, 1, 2, 3, 4, 5, so formal charge 6 minus 5 is 1, so there's a positive 1 charge here, formal charge. That is going to be your 71 over there. 72, what could that be? Oh, well, the difference between 71 and 72 is just 1, and so then 1 can only be a hydrogen. There's nothing else. I can give you just 1. So let's see what could be a possibility for 72. So this is not a very long chain, but you still have up to gamma, which means you can do a gamma cleavage. And we had a name for that, McLafferty rearrangement, and that's a possibility. Let's try doing one of those. All right, so here is your carbonyl, and that's your radical cation. And here you have 1, 2, 3, 1, 2, and then you have a third carbon here. This carbon would have a hydrogen, so that would go for a nice 6-membered ring here. So let's see what we can do with this alpha, beta, gamma. So here you can think of a cleavage like this. So here's your, we can even start here or here, it doesn't really matter. So here it pulls off your hydrogen. which means the hydrogen has to put its electron somewhere. It goes over here and breaks up this bond, which means these electrons are being pulled in by that oxygen there. Okay, so here this fragment, we're cutting it here, taking that out. That's your 2-carbon ethylene. So ethylene is going to be 1 less than an ethyl, which means it's going to be a 28, and 100 minus 71 is 29, 100 minus 28 is 72. So what do we have remaining here? So you have a double bond right there. Remember, there are 2 hydrogens here, so those are going to be sticking around. And here's your tail on the other side. This is now a single bond oxygen bonded to a hydrogen, and you have a lone pair here, and you have a radical here. Let's look at the formal charge of that oxygen. We can't miss even an electron here. Everything's got to be accounted for, all right? So here, what's inside the box? Let's count it out. 1, 2, 3, 4, 5. Periodic table says it's got to be 6. Therefore, there is a positive. So this is your radical cation, which is then going to hit that detector and give you a 72 peak here. All right, so that's going to be for your D, I would say. Let's look at what could happen if you cleaved it at B. So let's do B over here. So you're going to take the exact same radical cation of the molecular ion, and you are going to do the alpha cleavage on the other side, like we mentioned before. So here is your radical cation, and we can then put a triple bond here and send this propyl off packing as a propyl radical. Therefore, what's going to be remaining here is your carbon now having an sp triple bond here, and you got rid of that radical, and you have 5, 1, 2, 3, 4, 5 for the oxygen, which means 6 minus 5 is a plus 1, and that is going to be your M over Z. So here you're taking off, if propyl is 43, so therefore this is going to be a 57, which is right up here. Now you might think oxygen with a positive is really, really bad, and so how is it that it has such a high abundance? Even though you have a positive here, it is still obeying the octet rule. We told you octet rule in resonance, when you have to choose between a positive that has an octet field versus a positive that doesn't have an octet field. This is going to be a lot more stable because it has got octet rule. Okay, so I'm going to put obeys octet rule. So therefore, it's going to stick around, and that's why you see so many of them stacked up here to give you a relative abundance of 95%. All right, which only leaves this 43 here, and let's see what that could be. This is something that happens in ketones, and I'm just going to write it out here. So once you have your 71 here, this can break up further. You can see that in this 71 is hidden a carbon monoxide. And carbon monoxide's, you know, one of the biggest we call it a silent killer because it can be there and it can, you know, work on in your lungs and kill you, right? So let's go from 71 here. 71 is your carbon monoxide attached to a propyl carbon. So that is a possibility for this molecule. So let's see what could happen if you have a carbon monoxide going away. So here you can take this and you can see, well, your carbon monoxide can leave. So here is your carbon monoxide that has a positive charge, and so this can, you know, go over here. And so you can get your carbon monoxide, which is 28, and you can get a 71 minus a 28 is going to be your 43. Now, this is, you might say, this is a primary cation, but rearrangements are common, and this can go to a 43 can go to a secondary cation here. Okay, that's possible. And so that is 43 for you. Let's look at what other peaks are here. So we accounted for this. 29, 29 is basically a cation. And we can see, we can think of, well, here's an ethyl that can come out. Here's another ethyl that can come out. So many different possibilities for that molecule. All right. So let's look at your 29. Well, you can think of this as coming off of the radical cation. And here again, you can have a positive here. You can pull this off and have this go up, and that would be pretty stable. Or you could pull this up. Either one, you know, you're going to get a ethyl coming off. All right. So here you go. So once you take off these electrons, there are 2 hydrogens here and a CH3, and that is going to give you the cation peak. Positive. 1, 2, 3. 4 minus 3 is a plus 1. And you could think of this as having a fragment here. Now you have a double bond there, and your oxygen is going to get another lone pair. And if you do formal charge for this, this is going to be 1, 2, 3, 4, 5, 6. So it's a radical. 6 minus 6 is a 0, so there is no charge here. This is a 0 fragment that flies out of the chute. So this is your 29 m over z peak. All right. So we have 29, 43, 57, 72, 71, and 100. All of these peaks here. Well, I'm going to see you soon with another functional group. Let's do them all. Let's catch them all. Let's catch them all, the Pokemons. See you soon.